Hello everyone, I am Zhimin Fan from the Department of Polymer Science and Engineering, Harbin Institute of Technology, and I am very glad to have such an opportunity to communicate with you. The topic of my report today is the controlled construction and application of MXene materials. First of all, I would like to talk briefly about graphene because I would like to introduce the importance of studying machines and the material through graphene. As we know, in 2004, two scientists at the University of Manchester in the UK paired off a single layer of graphite or graphene by using adhesive tape. The discovery of graphene was uh, awarded the Nobel Prize in Physics in 2010 because it broke the classical theory that a perfect two-dimensional structure cannot exist stable and non-absolute zero. In fact, graphene is a material in which carbon atoms are tightly packed into a single two-dimensional honeycomb structure, forming a carbon isomer with graphite, carbon nanotubes, and fluorines. The properties of graphene are extremely excellent. Its strength is 200 times that of steel, which cannot be penetrated by bullets, and its electrical conductivity is 1.6 times that of zero. Therefore, graphene is called the king of materials. Based on the excellent performance of graphene, it can be used in almost all fields, such as supercapacitors, secondary batteries, flexible displays, and composite materials. At present, all countries in the world have introduced policies to develop graphene, especially the graphene battery. They are often having use of charging for a few minutes and a range of hundreds or even thousands of kilometers. Nowadays, many people think graphene is a scam. Then why is graphene so good in nature and so much worse in performance in practice? In fact, the vast majority of graphene in the market is not really graphene, and the biggest challenge facing graphene remains the difficulty of preparation. There are four main methods of graphene preparation: mechanical exfoliation, which involves turning graphite with tape, and liquid phase exfoliation, which involves exfoliating graphite in organic solvents using ultrasound. The disadvantages of these two methods are obviously one is extremely low yield and the other is poor quality. However, this method is difficult to transfer and extremely expensive. There is also the redox method, which is often referred to as the Hammers method, which is a top-down method where graphite is first oxidized to graphite oxide, exfoliated, and finally reduced to obtain graphene. This is our current method commonly used in laboratories and many domestic companies, but the graphene produced by this method has many defects and the performance is very low. But as a material, it must eventually go to industry and the market so that the material can benefit mankind. For example, in the semiconductor industry, the electrical mobility of germanium is better than that of silicon, but silicon is still almost the only material in electronic products because it is cheap, high in content, and easy to process. In other words, the law and the requirements of material development is still to be cheap, high content, and easy to process. Therefore, both graphene and the subsequent emergence of two-dimensional materials, such as silicon, are currently facing the dilemma of transition from the laboratory to industrial applications. Does that mean that two-dimensional material such block-neck cannot be overcome? Google C graduate students make through a MXene phase into hydrofluoric acid with perfectly etched over the aluminum layer and then ultrasonically poured it off to obtain a two-dimensional MXenes, opening up a whole new world of two-dimensional materials. However, the mix obtained by etching with hydrofluoric acid is a multi-layer organ shaped, and if you want to get a single layer, you need to pair it by ultrasonic method. But the yield of single layer is very low, and there are many defectors. Subsequently, in 2014, they developed a method to generate hydrofluoric acid in silt using hydrofluoric acid and ethyl fluoride, which can easily prepare monolayer MXene with high yield and few lentic defectors. So far, MXenes has entered a field of rapid development. Why MXenes can stand out from the rest and get rapid development? It is related to its unique properties. It is the only two-dimensional material that is both highly conductive and hydrophilic prepared by liquid-phase chemical method. Moreover, due to the rich functional groups and hydrophilic characteristics of MXene terminals, it has excellent processability, so people have prepared MX films, MX fibers, MX aerogel, and other MX macro bodies. Importantly, by scaling up the property of MXene in 2020, Google C found that the properties of MXene prepared in bulk are almost indistinguishable from those of laboratory grade, which creates a significant difference from graphene. Therefore, MXenes is one of the very few two-dimensional materials that have the potential to be industrialized. Of course, there are more than 20 types of MXene, and its diversity makes it show a wide range of applications in energy storage, electromagnetic shading, water treatment, electrostatic spinning, seawater desalination, therapy, and actuals. However, MXene assembly will be severely stacked between the layers of the sheet, which will cause difficulties in ion transport. MXenes is easy to oxide and has a short shelf storage period, which will cause serious obstacle to its markability. In addition, we still need to be explored in some new areas. What about my work in the past few years, which all starts around the above challenging faced by MXene? I started to study this material in 2015 and actually made real progress and breakthrough in 2018. 2017 was the year when we were unable to obtain the layer MXene, which made subsequent work impossible. Then we figured out a simple process to achieve the preparation of monolayer max by ourselves. Therefore, in the past 5 years, I have published several high-level papers in MXene, in top international journals in the field of chemical materials such as metal and advanced science, and received the attention of academics globally, the inventor of MXenes. After years of exploration and research, we have now achieved the preparation of high-quality MXene in batch and small scale, and have broken through the key progress from dispersion to slurry to thin film. Through atomic force microscopy and transition electron microscopy, we can see that the prepared MXene layer states can reach the macro level, and the surface is smooth and neat, without obvious oxidation traces. And this technology is in the leading position in the international arena. The arrangement of MXene film sheets obtained by fitting or scraping MXene is extremely compact and has excellent flexibility. Like other two-dimensional materials, MXene also has a high aspect ratio, which can significantly reduce ion mobility and decrease metallicity, especially for thicker electrodes, where this decline is more pronounced. In addition, MXene sheets face the disadvantage of several aggregation causing loss of active sites when building microscopic film, which is determinant to energy storage conversion. To address these above challenges, we construct a series of dense nano-continuous channels with fast ion transport by using electrostatic self-assembly to introduce ion hydrox nanoparticles into the MXene layer and embedding porous graphene into the modified MXene layer. A structure with both high density and coherent pores is formed to achieve an integrated electrode materials design with high volumetric capacitance and high density. As we know, the exposed titanium atoms on the surface of MXene obtained by etching from MXene phase are unstable and easily oxide to non-conductive titanium dioxide in oxygen-containing water, resulting in its short storage period, which is a major problem that in the industry needs to solve urgently at present. In addition, the MXene dispersion has a low concentration, in which cause a large amount of water has to be removed subsequently, making process extremely difficult. For this series of problems, after a long exploration, we have published the solution in journals such as Angora and ACS Materials. It has long been believed that MXene films cannot be moisture activated because of the low oxygen content and high stiff of MXene terminals. We have experiments demonstrated that MXene films can rapidly absorb and disturb moisture, can sense humidity and the fingertip, and can act as a non-conductor electrical switch due to their high electric conductivity, and have reinterpreted and revealed the constitutive relationship between max and humidity graders. This work has received high attention from international peers and has been followed up since its publication, and has laid an important theoretical foundation for the design and processing of intelligent flexible sensors and soft robots. In order to solve the problems of its oxidation, difficult processing, and high transportation cost of MXenes, We further discovered the highly hyd- hydrated phenomena of MXene sheets on the basis of uh, German application and successfully constructed a highly solder-content non-adhesive door magazine based this theory. This semi-solid magazine has high redispersibility, high flame retardancy, plasticity, and easy possibility. In the future, the semi-solid magazine door can completely replace max dispersion as a raw material for the preparation of all max-based materials, which is of great practical significance to further promote the commercialization of MXene. Another work to be proud is one that was just recently published in Matter. We know that MXene thin films are an extremely important macroscopic assembly of two-dimensional material laminars that show great commercial value in many fields. However, it is difficult to directly structure a complete multi-scale structure using MXene film and substrates. For example, it is difficult to scale MXene films once they are formed. In addition, it is extremely difficult to vertically aligning the laminar in MXene films to achieve faster ion transport. Based on the research basic, the relationship between water molecules and the next layers, we then propose the weighting concept of MXene films. MXene films can be diffusively arranged by free water between the layers with the assistance of water oxide and have a time-independent character. The process is irreversible outside the limitation period. We can see that the connected complex structure parts can be captured under the control of red light, and at the same time, water can be used as a weighing agent to explain the state of max film as well. Also, shape fixation can be active by using water vapor to release the stress in the max film. In the field of energy storage, both in academic and industry, it has been desired to vertically align two-dimensional material sheet layers on a collector fluid, but this has remained elusive so far. Inspired by paper rules, the embedded carbon nanotubes or nanocellulars between the layers of MXene films and reinforcement and isolator, and then used the weighting property of MXene to bend it into MXene rolls, and subsequently obtained electrical vertically aligned with the collector fluid by freeze cutting. It can be seen from the test that the vertical aligned max can maintain good capacitive behavior in with thick electrode and extremely high sweep speed. Therefore, this technology is expected to completely solve the problem of low efficiency of ion transport between max nanosheeters. In addition, the simplicity of the process is ideal for industrial production. That is the foundation for the development of compact energy storage. Of course, there are many areas of max that was of further exploration and deep digging, but I think one of the urgent problems that needs to be solved at the present is the turning water molecules between MXene's layer. MXene stands out among two-dimensional materials because of wet chemistry, but the detachment line of water molecules will lead to the loss of mechanical properties of macroscopic builders such as max films, which cannot be applied in practice. How to solve this problem? I think we should anchor max interlayer water molecules by external support materials, and this best external support materials is nanocellulose. Through preliminary experiments, we have found that nanocellulose can not only enhance max film, in fact, it also has the ability to balance the balance of max film interlayer water molecular absorption and desorption. Of course, subsequent optimization of multiple parameters is required and challenging. This is all that I have reported, and I think I thanks Science Father for the valuable opportunity.